Hey guys, today we're going to learn about black holes, and there's a lot that goes that's involved with that. So we're going to start off with how gravity behaves when we dig down inside planets, and then we're going to do a thought experiment of what would happen if we started to crush the Earth smaller and smaller. Then we're going to introduce the concept of escape velocity, which is simple but important when we're thinking about black holes. And then finally, we'll finish up with other weird things that have to do with black holes. So our goal today is to get beyond the oh wow uh, element of documentaries and videos about black holes and get to what they actually are and how they actually form. So it's not that complicated. It's very interesting, and you guys can definitely understand. Okay, so we're going to start off by looking at what happens to gravity inside objects. So imagine that we dug a hole all the way through the center of the Earth and out to the other side. So like when you were little and you went in your backyard and you tried to dig a hole all the way to China, what if you actually succeeded and dug a hole all the way through? Now we're going to assume that it's not molten inside and that the sides of this stay open and all that. So despite my distorted drawing here, we're going to also assume that it goes directly through the center and out the outside. Okay, now, so if our guy here jumps in, he's going to start falling. He's going to fall and go faster and faster and faster. We're also going to assume there's no air resistance. So we're keeping this simple. And when we think about it, what's going to happen when he gets to the center? Is he going to splat there? Or more likely, is he just going to go shooting right on through and start heading up the other side? And the answer is, when you think about it, yeah, he's just going to keep on falling. He's going to go right through the center of the Earth because there's nothing there to stop him. And he's going to start going up the other side. And once he passes the center of the Earth, he's going to go slower and slower and slower because now he's working against Earth's gravity. So it's like he's going upward, but toward China. He's going slower and slower and slower. And in a perfect world, he would stop right when he got to the opening on the other side. And then he'd be able to grab onto the side of the hole and climb out. And he would be all the way on the other side of the Earth. And for trivia's sake, that would take about 45 minutes. We'll talk about how I know that another time, but it would take about 45 minutes to fall away all the way through the center of the Earth and out the other side. That would be a pretty efficient way to travel. But let's suppose that instead of just falling, he was climbing down a ladder, or suppose there was actually air resistance, so he reached terminal velocity. But when he got to the center, then the air would he wouldn't be going fast enough to go all the other side, and then he'd oscillate back and forth, and eventually the air resistance would have him stopped exactly there in the center. Now the question is, what would he experience there? And think about that for a moment and pause the video if you want to, but what would he experience there? Would he be like crushed down to a dot because the gravity of the Earth is pushing him in from all sides? Or would it be just like he's standing on the surface of the Earth? You know, he'd be able to put his feet on the the side of the tunnel and stand up just like he was standing on the surface of the Earth? Or maybe he'd be weightless. Maybe he'd just float there as if there was no gravity at all. Okay? And that's actually the answer. He would actually float there as if he was just in free fall out in space with no gravity around. Well, he's not even in free fall. There truly is no gravity there. Now, the reason is because, as you know, gravity comes from mass. So when he's here in the center, he's got half the Earth over here with its gravity pulling him that way. But he also has the other half of the Earth over here pulling him that way. So the gravity to his right cancels the gravity to his left. And there's also Earth between us and him and behind him because he's gone through the hole in the center of the Earth like the core of an apple. So everywhere, below him, above them, in front of him, in back of him, to each side, there's the same amount of matter in all directions. And all that matter is going to exert gravity on him in equal force in all directions. And keep in mind, it's not going to be like he's on the rack being pulled, on one arm this way and one arm that way. That gravitational force is acting on every molecule of his body and pulling each molecule evenly in all directions. So we'll all cancel out and he will just float there like he's out in space with no gravity at all, which is a weird thing to think about. Now, what about when he's part way down? When he's partway down, there is still more mass below him than there is above him. So he's still going to feel a downward force, but it's going to be less force than he felt when he was standing on the surface. Because when he was standing on the surface, all of the mass was below him. There was no mass above him pulling him back up and canceling that out. So if he's partway down, he's going to feel weaker gravity. And the farther he gets, the closer he gets to the center, the weaker and weaker the gravity becomes until he gets to the center, and then there's no gravity anymore. So the weird thing about this is that for any solid object in the universe, the gravitational force is strongest right at the surface. If he goes up above the surface, now he's farther from the center of the planet and gravity is weaker. We learned that in a couple lessons ago. When you get farther from something, the gravity gets weaker. So if he goes up above the surface, gravity gets weaker. But if he digs down below the surface, gravity also gets weaker. So again, the strongest gravity is exactly at the surface. Now that assumes that the object is constant density. Now in reality, they've done the calculation and it turns out Earth's gravity is strongest about 1/2 mile below the surface. So you got to dig down into a mine about 1/2 mile, and that's where the gravity will be strongest. And that's because the densest material in the Earth, the iron and nickel core, is down at the center. And the lighter stuff floats up on the top, like the granite and the rocks and stuff that the crust is made out of. That's lighter, less dense material. It's up at the top. So you have to be slightly closer to the center to get the maximum gravity, but you get the idea. If the object is constant density, the strongest gravity is right at the surface. Okay, that brings us to black holes, believe it or not. So this is kind of the pop culture version of it. A black hole is just so small that not even light can escape. There's Maggie Simpson getting sucked into a black hole almost. What we want to get to is the yeah, but why part of this. Okay, so to start off with this, we have to think about how black holes form. And as most of you know, black holes come from collapsing stars. That's where most black holes come from. And the reason that this happens is because there are nuclear reactions inside a star when it's shining. And those nuclear reactions are trying to blow the star apart and blow it out into the universe. So there's an internal force pushing outward. But meanwhile, the mass of the star itself has gravity pulling it all together. So the size of a star is determined by the balance of these forces between the fusion inside pushing everything out and the gravity outside drawing everything in. And you get some balance of those forces, and that's how big the star is. However, eventually the star runs out of gas and the nuclear reactions stop, and then the star begins to collapse. It compresses. It's like squeezing a sponge. It's the same amount of material, but it's jammed into a smaller volume because the gravity is pulling everything together and there's no force pushing it out. Okay, so an object will contract and get smaller and smaller as it goes. Now, let's think about what this means. So suppose we had the Earth and we collapse the Earth to 1/4 of its normal diameter. So here's the regular Earth, and we're going to put a 1 Newton weight on there. I think you can read that. That says 1 N, so 1 Newton. Now, if we compress the Earth so there's only half the diameter, and remember, we're keeping all the same amount of mass. We're just squeezing it like a sponge. We're compressing it into a smaller volume. So there's the same amount of material producing gravity. It's just in a smaller volume. Now, if it's half the diameter, we can apply our inverse square law, which you learned before. So now this mass is half as far from the center of the Earth as it was before. So if it's 1/2 of the diameter, it's going to be 4 times the weight. So it's going to be 4 newtons, right? That's inverse square law does it. Now, what if we crushed it all the way down so the Earth is 1/4 of its diameter? Hopefully you know that you can figure this one out because you've done inverse square law. Okay, if it's 1/4 of the diameter, we turn it upside down and square it. So it's going to be 16 newtons. It's going to be how much that weight weighs if we go to 1/4 of the diameter of the Earth. What if we take it even farther? What if we go to 1/10 the diameter? It's going to be 100 newtons, 100 times the weight, and so on, all the way on down, okay? So what we're seeing here is that the maximum gravity the body that a body can produce depends on its density. If we have the same amount of material jammed into a smaller volume, it can produce larger gravity. And as we saw before, that gravity is greatest right at the surface of the object. If we take the Earth down to 1/1000th of its diameter, it's going to be 1 million newtons. 1,000 squared is a million newtons. So maximum gravity depends on the density, and the object's greatest gravity is at its surface. Those are both relevant things. Okay, so we have one more piece of this puzzle to put in. So keep that idea of gravity increasing as the density increases. Just set that aside for a moment. We're going to come back to it. Now we have to get to this idea of escape velocity, or the question of what goes up must come down. So here we have the Earth, and we've learned and we've been assuming in all of our physics so far that if you throw something up, the gravity of Earth will pull it back down. So what goes up must come down. But we are always assuming when we say that, like a baseball in the classroom or a paper rocket out on the football field, that the Earth's gravity is constant no matter where you are, how far away from the Earth. And that's fine for baseballs and paper rockets because they don't go up very far. But if you think about it, if you're talking about scales on the size of the Earth, if you go up a long, long way, a couple Earth diameters up here, the Earth's gravity is significantly weaker up here than it was at the surface. So that means that if you throw something hard enough, it's going to go up to where the gravity is weaker. And then it can go farther because the gravity isn't as strong pulling it back. And as it goes farther, the gravity gets even weaker. So it kind of makes sense that it might be possible to be going fast enough that you just keep going and never come back. And it's true, there is a speed that you can go that can happen. So an escape velocity is the speed needed to escape the planet and never come down again. And for Earth, that speed is about 11,200 meters per second. Okay, so 11.2 kilometers per second. Now that seems like a pretty high number. But remember, we learned that to put something in orbit, you have to go 8,000 meters per second, 8 kilometers per second. So this is really not that much faster than going to orbit. If you can get up to 8,000 meters per second, you'll go up and not come down. If you go basically 3,000 meters per second faster than that, you'll go away and never come back, right? Now, another way to think about this is, what if we took our baseball or whatever this object is and we moved it an infinite distance away from the Earth? Okay, or an almost infinite distance away from the Earth. Newton's law of gravity says that there is still a force of gravity between the Earth and that object. It's very, very small, but it exists. Now, if we let the thing go and let it fall from almost infinitely far away, it's going to go faster and faster and faster and faster, and eventually it will hit the Earth. But it's not going to be an infinite speed. It's going to be going as fast as it goes. And it turns out that that speed that it would be going if it fell from infinitely far away would be 11,200 meters per second. That's how fast it would be going when it hit the Earth. So conversely, if you fire a projectile or a cannonball or something at 11,200 meters per second, it will go infinitely far away. And if you go faster than that, 11,300 meters per second, it's still going to be moving when it gets infinitely far away. So that's the escape velocity. That's the velocity you need to escape the Earth's gravity forever and ever.